So, thank you very much to everyone that is here. We're not a lot today, but let's try to have some fun with this. So this talk is going to be a little bit different from all the others that we've heard today and the other days, because we are not here to present a product in itself and, and to sell it to you somehow. We're here to present a project that it is expected to fundamentally change the way we generate and distribute electrical energy. It is expected to fundamentally change the concept around transformers and machines. And it is about moving the technology of silicon carbide to the same stage of development as the technology of silicon today, and making a whole new set of devices, electronic devices, that will go directly in the power grid. So this is what I'm going to say, a brief outline. I'm going to present the consortium. I work for a company, but I'm not here representing that company. I am representing 17 entities that are cooperating together in this project. Then I'm going to very briefly show you why silicon carbide is needed, what are the advantages of silicon carbide in front of silicon. Then I'm going to talk about what are the goals, and more specifically the goals of the project that are relevant to this symposium here, because there are many different goals, but I took into account the specificity of this symposium. And then I will describe briefly the project and the strategy that we aim to follow over the next 4 years, which is the duration of the project, to achieve those goals. Well, who we are. We're 17 entities coming from 9 different countries in Europe. Some of them are as well-known and as large as ABB or Infineon. Some of them are small companies, such as Norstel, Ascatron, INAEL. Many of them are actually institutions, research institutions. The Fraunhofer, that is going to talk here right after me, is one of our partners in this project. And the University of Nottingham and the University of Prague. We also have a very large power utility, INAEL. You probably know them. They are the utility distributing energy in Italy and in many other parts of Europe. So, like I said, 17 entities from 9 countries working together to bring about this new generation of silicon carbide power electronics and to try to change the way we distribute electrical energy. So, why, oops, okay, good, now it's better. Why silicon carbide? What's the issue? Well, there are many semiconductors around. You probably know that. Many people talk about gallium nitride, gallium arsenide, silicon carbide, diamond, for example. Diamond is a very promising semiconductor, but each of them has, a niche. Each of them has a space. So in order to go to energy applications, high voltage, high temperature, high power, what we did is we focused on silicon carbide because the crystal properties of this material make it optimum for that. We submit a proposal. We were in competition with some people that were trying to do roughly the same thing with other semiconductors. And apparently, the people that actually evaluate those proposals somehow thought that, in fact, silicon carbide has the best options, the best chances, and this is because it is high temperature, high power, high frequency. So we can do things at a much higher frequency than with silicon, which allows us to reduce enormously the size of the things. So essentially, transformers or machines of all type can be reduced a factor of 10. It is a very high temperature device, so you can put these kind of things closed under the sun in the top of a tower, whatever, and it's going to work perfectly well. And it is specifically good to be applied under high voltage conditions. Well, so what are essentially the goals of the project? I'm going to go very quick to the heart of the matter. I'm going to explain in a little bit more detail the project later, but the thing that I want to say very quickly is what is the main practical thing, the main result beyond semiconductor technology, making wafers, improving crystal quality, things like that are probably not so important here in this forum. What is the thing, the practical thing that we want to achieve? Well, the practical thing that we want to achieve is a new generation of power converters both like inverters, like those ones that go in solar farms or in wind farms, and also transformers that will be entirely and completely electronic. So in a sense, you would say, well, many of you may be manufacturing for conventional transformers, maybe manufacture transformers or components for them. So it is important to understand that this is not in competition. It's not something that is trying to take away the market for you. It will create new markets as distributed generation and renewable energies go widespread. Then this kind of devices will have a new possibility, will create new possibilities and new markets, right? It's not intended to completely substitute the normal transformers by this kind of electronic silicon carbide-based devices. So what we're going to do? Well, we're going to do this kind of things, which is essentially a solid-state transformer. Then we're going to try to pack this thing into what we call intelligent distribution substations, which will include not only the transformer itself, which is this thing here, but also storage and direct connection of renewable energies. And then we will finally try to pack this thing into some kind of whatever, maybe containers, maybe concrete buildings, maybe whatever. That would be the final system somehow seen in many other places, similar to the type of substations that you see in distribution. And that is essentially the final target of the project. Now, this being said, which is the core of the idea, I will explain a little bit more detail what we're going to do to reach that point. This point is at least 4 years in the future. That's the truth. It is at least 4 years in the future because the project has started this month, January, and it is a 4-year project, so that's not going to happen immediately. There is a lot of work to do. And the way that we will follow to achieve these goals will start with the material. First of all, we have a lot of scientific and academic issues to resolve, to grow silicon carbide wafers, to process silicon carbide wafers, to manufacture power devices that are going to be up to 10 or 15 kilovolts themselves. Just think of one transistor that you have in your computer or your mobile phones, one MOSFET, right? One MOSFET is typically, what, 100 volts, 200 volts? We're thinking about making MOSFET 15 kilovolts, a 15 kilovolts MOSFET that can go directly in the grid and will be able to act as a solid-state switch and to completely change the way the grid is managed and will make happen this idea of the smart grid, okay? So then, of course, once we're able to manufacture monolithic transistors of 10, 15 kilovolts in this silicon carbide material, then it will come the whole packaging and reliability. So you have a transistor in your, in your lab, and now you have to package it, and you have to test it, and you have to show that that can go in the power grid. And then finally, we will target the applications in energy, which is exactly what I started talking about. Energy converters for generation, transmission, and distribution. This particular project does not cover applications of silicon carbide to traction or to other areas where it will be also applied. But what we did is we didn't want to say we will solve all the problems of the world in one project, right? So we didn't have that capability. So there are many applications of silicon carbide, specifically traction or automotion in some sense, that we do not cover. And there is room to incorporate new ideas or new people somehow that could cover those aspects that we do not. Okay, so essentially the main ideas is this, for example, this is a typical silicon carbide wafer. This is a typical MOSFET. It's maybe 100 volts, right? So just imagine that 150 times bigger and with an enormous quality of the material so that you have no failures. So that is what we are targeting. So what is for? I am repeating myself here because I wanted at the very beginning to show you this change in the concept, this idea that everything will be electronic in the grid in the future. But I come back now to why. What for? So why do you want everything electronic? What's just because that's fashionable? What's the idea behind? So the idea behind is an enormous increase in energy efficiency, an enormous increase in the capability of penetration of renewable energies. So silicon, an electronic grid based in silicon carbide will allow seamless integration of very many different types of distributed renewable energies that today are not so easy to integrate in the grid. A superior power quality, of course, that is very important because silicon carbide can handle and can reduce and smooth down harmonics and can improve power quality in the grid enormously versus what happens today when you have a wind farm and you inject energy through a typical silicon converter that introduces an enormous amount of harmonics and distorts the signal. So that will not happen with silicon carbide. And ultimately, last bottom line, we will try to do cost savings. Well, it's not that we try, it's the target. The target is save cost in equipment, save cost in energy losses, save cost all around the grid, save cost by increasing energy efficiency, and hence potentially reducing, having the capability of reducing the price of energy, which, of course, our partner INAEL does not want to talk about that, but that will happen sooner or later. Okay, so again, the stage in which we are now, today, we're working essentially in this part, in the silicon carbide substrates, in the epitaxial layers, and in the semiconductor growth technology. So we are at the more fundamental level right now. We're starting the project, and we're making the material better. Just think that silicon has 60 years history, 70 years history. So we are still far away from being able to do with silicon carbide what we're able to do with silicon. A silicon wafer is very easy to produce. You can produce millions of them at a very low cost, right? Today, for us to produce a silicon carbide wafer is not so easy. It is expensive, and we're moving the technology towards the point in which you can really produce at the same cost and with the same efficiency as you produce silicon. So we are at this point. And of course, we're starting to design what I showed before, which is these two applications, a cost-efficient and competitive solid-state transformer that will be based on 15 kilovolt devices and will be directly on the grid, and also a wind turbine-specific new type of power converter, again based in silicon carbide, which will improve efficiency enormously, will provide a much better power quality than silicon-based converters. And this is starting to be designed right now, but it is still, say, on paper, because that is the end of the project, to demonstrate that. Well, we tried to cover the whole value chain in the project, in the sense that we are vertically integrated from people that actually produces wafers, people that are like, imagine Intel, but like 1,000 times smaller or 2,000 times smaller, right? But it's people that is actually producing wafers and material. And we move from that to people that integrates that material in devices, in MOSFETs, in transistors. And then we have the people that actually does the testing and the reliability and the qualification process so that you can actually put these devices in the power grid. And we finally have people that will actually implement this new type of devices in the wind power converter and in the solid-state transformer. And the potential client, as this Italian utility, INAEL, whose role in the project is actually to be the end user, the final first tester of this kind of devices that will be installed in real-life applications in Italy, most probably. So we try to cover the whole value chain, and essentially, what we did is to articulate the project around 3 core concepts: materials, devices, and applications. Like I said, again, it's the same I said before. Materials is what we are doing now, improving silicon carbide. Then we will move to devices. Devices is, again, what I said. It's just with a good wafer of silicon carbide, good quality, low cost. Now you have to produce a 15 kilovolt MOSFET. To produce a 15 kilovolt MOSFET, you need a thickness of the wafer that may be up to probably 150 microns. To grow 150 microns of perfect crystal is really complex and difficult. So this is say, the devices part. So give me a good wafer, and let me see how can I build a 15 up to 20 kilovolts single transistor or diode. Imagine a diode of 20 kilovolts. That would change completely the way you transfer, distribute, and transport energy. And finally, of course, like I said, the applications, which now lie a little bit far away in the future. There is nothing tangible in the applications right now. There is something tangible in the materials, not in the application, but that will come in the forthcoming years. Well, and this is essentially all. I don't want to bore you more with some details, because what I have here is a list of working packages, a brief description of the working packages, how the project is articulated. But this is thought a little bit more for a more, how to say, academic audience. So I don't think at this point this is very interesting. So of course, you are free to ask. This is a publicly funded project. There is no secret here. There is a web page, actually. I'm going to skip directly to the web page. Here it is. So there's a web page where you can be constantly informed about the things that are being done, the dissemination, and the papers that are published. Some of them are very academic. Some of them are much more, for people of all kinds. And of course, any questions, any ideas, or any suggestions are more than welcome. And with this, that's all I wanted to say. Thank you very much for your attention.